So far in this chapter, we've looked at how logs are exponents. We've also looked at how the graph of logarithmic functions are the inverse of the graphs of exponential functions. But we've missed one key piece, which is that logarithms can be used to solve exponential equations. So if I look at something like this, earlier on in the chapter we said, well, if x is up in the exponent, I might not really know how to solve this equation. So I could graph the line y equals 8. I could graph the exponential function y equals 16 to the 3x. And then I'd look at where these graphs cross by doing a second calc intersection. And while that was one option, we also noted that, well, if I could rewrite both of the sides of this equation so they have the same base. So for instance, 16 can be written as 2 to the 4th. So this is 16 to the 3x. 8 can also be written as a base of 2. If I can rewrite these as the same base, well, if 2 to the 3rd equals 2 to the 12x, then at this point the exponents have to equal each other. So x would have to equal 3 over 12 or 1/4. So those are two methods to solve this equation. Now, what if I don't want to graph the function, and what if I can't do something like this, where I can't rewrite both of these terms as the same base? Well, then that's where we have to recall the three properties of logs that we studied in the previous section. So we talked about how, okay, well, if I have logs of the same base and I'm adding them, that would be the same as if I was originally multiplying 3 times 5 and said log base 10 of 15. So remember, this is a common log. If I add exponents, that happened when I was originally multiplying terms with the same base. If I was subtracting logs, well, a log's an exponent. So when do I subtract exponents? If I was originally dividing terms with the same base, so I could combine those into one by dividing the arguments. And then this third one is really the property that we're going to look at today. We had said, well, if I have a number out front, that's the same as bringing it up to the exponent on the argument. And I could say this is log base 2 of 4 to the 3rd power. And then, of course, I could go in reverse, where if I was originally given this, I could bring that exponent down out front, and that should equal 3 times log base 2 of 4. This last property is the one that we're really going to be keying in on today. So now, what if I can't rewrite the equation so the bases are the same, like I did on the warm-up problem? Well, I want to find x. So the 2 is attached to the exponent, nothing else is. So first thing would be get rid of anything that's not immediately attached to the x. So in this case, I'm going to divide each side by 6. 72 divided by 6 is 12. Now, note that I can't write 12 as a base of 2. 2 to some power, or 2 to some integer power does not equal 12. So off the top of my head, I can't change these so they have the same base. I could go ahead and graph these and find the intersection, or I could use that third property of logs. So at this point, what I'm going to want to do is I'm going to want to take the log of each side of the equation. So what I do to the left side of the equation, I have to do to the right side of the equation. So what's happening here is if 2 to the x equals 12, then log base 10 of 2 to the x would have to equal log base 10 of 12. If these expressions are equivalent, 2 to the x still has to equal 12. So I haven't changed the value of anything, but why would I want to take the log of each side? Well, in the end, I want to end up freeing this exponent. So if I take the log of each side of the equation, then I can apply that third log property and bring the exponent out front. So now I have x times the log of 2 equals the log of 12. Now this is all attached, that's just a number. So at this point, I want to divide by the log of 2. So to get x by itself, just divide by the log of 2. Anything divided by itself is just 1. Please do not say this is log of 6. This is saying 10 to what power is 12? 10 to what power is 2? And I'm dividing those two numbers. It's not equivalent to the log of 6. So now you just go to your calculator and type in log base 10 of 12. So log of 12 divided by log of 2, and that should spit out your answer. So we're definitely going to be using our calculator in this section. If I round to the nearest hundredth, I get about 3.58. Now, since you can use your calculator, please go back and check. If I plug this into my original function and take 6 times 2 to the 3.58 power, I should get out just about 72. It might not be exact because I have rounded my answer. So why don't you give the second example a try? I want to solve for the variable up in the exponent. I cannot rewrite these so they have the same base to an integer power. I could graph these on the calculator, but let's do this without graphing. Let's do this by taking the log of each side of the equation. So start there and let's see how far you can get. Pause the video. So I started by taking the log of each side of the equation. What I do to the left, I do to the right. If these logs are equivalent, the arguments would still have to equal each other, so I haven't changed the value of anything. That allows me to bring this whole exponent out front. So now I'd be at this line. If I want to get x by itself, well, let's get rid of multiplying by the log of 15. So I'd want to divide each side of the equation by log base 10 of 15. This would just cancel out. So then I would have 3x minus 2 equals log of 285 divided by log of 15. And eventually I would want to add 2 and divide by 3. So to find x, I would have all of this stuff, whatever that is. Go to your calculator, type that in. Then to get rid of subtracting 2, I'd want to add 2 to that. And then the last step, I'd want to divide all of this stuff by 3. So let's go to the calculator. I can do a common log on the calculator. Log base 10 is what we're looking at. So I have, what, log of 285 divided by log of 15. Then I'm going to add 2 to that. And notice I'm hitting equals here because I want to add 2 first, then divide by 3. And I'm getting out about 1.36 for x. I'm so careful on your order of operations. If you type this all in at once, make sure you do all this stuff in the numerator first, then divide by 3. And again, it won't be a bad idea just to go back to your original expression, plug in that value of x, since you can use your calculator, and check to make sure you actually get out about 285. Now, this is an example that we did at the beginning of the chapter, and I said, well, right now we only know how to solve this using the graphing feature of the graphing calculator, but later on we can use logs to solve it. So if you would, write the equation. If you purchased a car at $15,900, it depreciates at an annual rate of 11% each year. And I want to know in how many years it will be worth $10,000. Let's write the original equation, pause the video, and check our answers with each other. So here's my starting equation. This is my principal amount. I'm losing 11% each year, which means the car would be worth 89% of what it was the previous year. It's depreciating, it's multiplying by 0.89 every year for X years, and I'm getting out $10,000. So that's the equation we're looking at. In the past, we go to the calculator, graph these two parts, see where they crossed, and get the value of X. You could certainly do that, or you could use logarithms. In your homework, I ask you to solve these using logs, so I want to see the work of how you'd use logarithms to do this. So if I want to get x by itself, well, I mean, there's a couple things that are not attached to x. If I look here, actually just this one thing. So 15,900, that's not attached to the exponent. So at this point, I could certainly go ahead and divide each side by 15,900. So now I'm at this point, I've got rid of anything that's not attached to this exponent of x. How do I free up a variable in the exponent? Well, this is where logs come into play. By the way, I could cancel a couple things here, so if I wanted to cancel a few zeros and simplify that fraction, feel free to do so. I'll just leave it like this for now. So if I want to get x out of the exponent, this is the point where I would take the logarithm of the left side of the equation, the log of the right. Remember our base is 10 here. I'm taking a common log, then I can use that button on my calculator. That allows us to free up the exponent and bring it out front. So now I would have log of 10,000. And I'm taking the log of all of this stuff. So it's the log of 10,000 divided by 15,900. It's not the log of 10,000 divided by the log of 15,900. So this whole thing is your argument. If I bring the exponent out in front, on the right side, I would have this. And now the last thing I'd have to do to get x by itself is divide by the log of 0.89. So why don't you go ahead and type this into your calculator and let's see if we get the same answer. So I'm going to type in log of 10,000 divided by 15,900. All of that is in the first parenthesis. Close that parenthesis off, then I'm dividing by log of 0.89. Close that off. And I'm getting out about 3.98 years. So this seems reasonable. In a little less than 4 years, the car will be worth $10,000. Now, the second big idea from this section leads us to what's called the change of base formula. So let's evaluate log base 7 of 55. So I want to know, well, log base 7 of 55, I want to know what the exponent on 7 would be that would give me out 55. So this essentially means 7 to what power equals 55. Well, now I don't know what this is. 7 squared is 49, so x might be something a little bit over 2, but without using my calculator, I can't really solve this. So how do I free up x in the exponent? Well, if x is in the exponent and I want to solve this, I should just be able to take the log of each side. So I have log base 10 of 7x equals log base 10 of 55. And again, I'm using the common log because I can just punch that button in on my calculator. That should allow me to bring the exponent out front. And then last thing, divide by the log of 7. And I get the log of 55 divided by the log of 7. If you go ahead and punch that into your calculator, log of 55 divided by log of 7, you get out, yep, something just a little bit over 2, or about 2.06. So x is approximately equal to 2.06. Check that out. Is 7 to the 2.06 power about 55? Yes, it is. Now this actually leads us to what's called the change of base theorem. I can jump straight from here down to here every time. So let's say I gave you something like log base 3 of 19. You could go through all this work and say, well, 3 to what power is 19? And then I take the log of each side and I bring the exponent out front. And then I divide by log of 3. Or I could skip all these steps and say, if I see something like this, the log of the argument divided by the log of the base. So log base 10 of 19 divided by log base 10 of 3 should be equivalent to your answer. That's called the change of base theorem. So for all positive real numbers, A and B, where where B is not equal to 1, so the base can't be 1, has to be positive, and the base here can't equal 1, has to be positive. I could say, well, if I have log base, well, I don't know, 8 of 50, that equals the log of any base, I'm going to say base 10 since my calculator does that, of the argument divided by the log of any base, again I'm going to choose base 10 for that button on my calculator, of the original base. So this is essentially the change of base formula. Log base 8 of 50 equals log base 10 of 50 divided by log base 10 of 8. Now you might be thinking, maybe you've discovered that you can also do this on your calculator. Yes, you can. So let's look at this example right here. So log of 50 divided by log of 8 is about 1.88. Now, if you have the new operating system, you can do logs of base other than 10. So if you go to catalog, which is right above the 0 button, and scroll down to the L's, you can see log base right there. So if you choose log base, we did what? Log base 8 of 50. This is another option that should give you the same answer. So if you have the new operating system, yeah, you can kind of shortcut this change of base formula and just go to the catalog feature right here. Or if you don't have the new operating system, you'd have to know that change of base formula and say log of 50 divided by log of 8. So last two examples, why don't you give these a try using the log properties and the change of base formula. Pause the video, then you can play it and check your answers with me. All right, so here are the answers. You could combine this into one log by multiplying the arguments. I have log base 3 of 100. If you use the change of base formula, then you could just take log of 100, which should be equivalent to 2, divided by log of 3, and you should get out about 4.19. At this point, could have you done something like this and solved by taking the log of each side and dividing? Yes, eventually then you'd get to this point and you should get the same answer. Second equation, bring that exponent or that number out front up to the exponent on the argument. If I'm subtracting logs, you could divide the arguments to create one log. So I'd have log base 9 of a third. And well, hey, 9 to the 1/2 is 3, so 9 to the negative 1/2 would be 1/3. This one you actually don't even need a calculator for, but if you want to check, this should equal log of 1/3. So if you did use your calculator, maybe you type this in, and yeah, that should give you negative 1/2 for the answer.